So hello everyone, and I hope everyone is well. So I'm going to make some video for chapter 21 on the Black-Scholes model. I had intended to do a lot more, but it's a little difficult in this thing we're doing here with the online to do that. So I'm going to go over some slides on chapter 21. You won't be responsible for a lot of the math in here, but I just want you to understand the terminology and the concepts that go on with options, all right? So options are contracts, as you all know, and back in 1973, there really wasn't an options market. It was very small until two guys by the name of Myron Scholes and Fisher Black developed what's called the Black-Scholes option pricing model. And from this point on, the option industry took off. And there's a great movie called $1 Trillion Bet. And I suggest if you ever have a chance, you watch it. It's only about an hour long, and it's a great thing on the history of how the option industry was born. Okay, so we're going to talk about the binomial model. Now, the Black-Scholes model is an equation. It's a simple equation that we can throw into Microsoft Excel and solve. It's actually very simple. You put about 5 inputs in there, and it pops out. What the Black-Scholes model does, it'll tell you the theoretical price of a call and a put on a European option. Now, it was very basic. They had a lot of assumptions with their model. And when they came up with this model, of course, the industry was born. And from that point on, an industry grew in what was called option pricing models. They had to make better models and make a lot more corrections so they can price American-style options and stocks with dividends. So basically, scientists and physicists decided that they'll go to Wall Street and write option models to improve on the Black-Scholes. They'll make a lot more money than they would doing science. So this is a short history of the Black-Scholes equation, but this suffice it to say, this was the model that made it all take off. And what I want to also drive at is there's also models called the binomial option pricing models, which is not physically an equation, but it's a computer method to price an option. Now, the important thing you have to know is if a option, a call, or a put does have a price, any model must give you the same price, right? Or you would have some kind of problem with the models, right? You can't have different prices for different models, right? An option has a price and it's a set price and that's it. Okay, so we're going to talk about that, and we'll look at just a general idea of these models, and I'll try to find some other things we can add to the video here. But you can always go to YouTube also. There's always millions of things on options on YouTube and everywhere else. I believe I have a lot of papers on Black-Scholes and the binomial model on the blackboard. If I don't, if you want any, just let me know. I'll put some up. Okay, so we're going to basically look. So here's the whole idea. The law of one price to explain how the binomial option pricing model provides the correct value under the assumptions made by the model. So remember, the law of one price tells you what? That no matter what model you use, an option or any asset has only one price. So you can't have different prices for different models, all right? So, I mean, that's the underlying theme here, okay? And then we'll look at the binomial, in an introductory way, and then we'll look at the Black-Scholes model to calculate the value of a call option. And you'll notice here on a non-dividend paying stock, and basically it's a European option, okay? And there's a little redundancy here, but so basically they say use the Black-Scholes option pricing formula to calculate the price of a European put option on a non-dividend paying stock. So they basically do the call and the put. And they're a little, this should say, value and call is the same thing, but we should be consistent, right? So we should say the price of a call option and the price of a put. And this should say European call. So we should make sure we have a consistency here, right? And they seem to match pretty well now. So we'll get that done. And then we'll look at, rather quickly though, the price on a dividend paying stock. Right, that gets a little more complicated. All right, so we'll go through those. All right, so the binomial model, and again, please look at the definitions and terms that are important here. I'm going to hold off on the mathematics. This is simply a technique for pricing options based on the assumption that each period the stock's return can be taken on only two values. So they create a value tree, okay, for stock prices going up and down. And here's what I'm talking about. There's a binomial tree, and there's two branches at every point in time. And of course, it's computer intensive, so you can't do this by hand. You can only do 2 or 3 by hand, and we would have done that in class, and I think a lot of people are tired. So and basically again you need the law of one price, right? Again, let me see if I could fix that. So you need the law of one price to basically tell you that the current value of the call and the whatever portfolio you put together to replicate it has to be equal. And also if you use the Black-Scholes model, right? So either way, you've got to have one price. So what's the definition of a replicating portfolio? It's a portfolio that consists of a stock and a risk-free bond. So you should know this term, right? Like for a true and false equation, right, on the final. So a portfolio consisting of a stock and a risk-free bond that has the same value and payoffs in one period as an option written on the same stock, all right? All right, so basically they go through in the book a two-state single period model. And there's a lot of math involved here. And you can see they start moving the stock price up and down in different levels here, right? The stock price moves up and down in different levels. And they start trying to, and what their ultimate goal is to determine the price of the call, but to determine the price of the call here, right? That's what you want to know. What is the price of the call at time t0? You know the price of the call at expiration, right? That's obvious, right? Because the stock is up to 60, so you got intrinsic value of 10, and here you're in the money here, right? Here you're out of the money. So anyway, they've got this two-state model that they go through, and I'll skip over some of this math. So here's the important thing. The important thing is by using the law of one price, using what they just accomplished, you can solve for the price of the option at the very time t0 at the beginning without knowing the probabilities of the states in the binomial tree. Okay, so you don't have to know the probability of the states. So that's an important concept, all right? So again, that's a nice true and false question that you should understand that terminology. So again, here's some examples, and they start going through generalities now with the math without numbers. And again, what they're trying to accomplish is if the stock moves, they want to know the value of a call here. This is all very computer intensive, and they're just showing you how this is done in a very simple sense with only a couple up and down movements. And here they are generating the replicating portfolio in the binomial model. And here they are actually determining the value of the option in the binomial model, right? So again, this is done at the original time you bought the stock, and you want to know how much is that call or that put, that respective call or put. Okay, so it's an important idea. And they go through this again with now with a put option. Okay, they do the in the textbook example, they'll price a European put option. Remember, it's easier to do Europeans because they're not. You can't exercise them at any point until expiration, and the math became intolerable for them if you could exercise the put or call at if it was American at any other point in time. So it made it real easy for them to do the mathematics on a European option. All right. So anyway, you can if you go through this math if you're just interested, and you can see now they have a multi-period model here which they go through, and now they're adding more periods. And again, here's the stock changing prices up and down. And again, it's a very simplified model. And again, what they're looking for, either what's the value of the call or what's the value of the put, right at this point in time, T0, right? Because you know it at expiration. So you got to do it in multiple steps. You go through multiple steps. So you got, again, what's called the multi-period model here. And it lends itself easy in Microsoft Excel to do all this. So I want to move on to now the Black-Scholes model. So the Black-Scholes model, as I said, came about in like 1973, and ultimately, 25 years later, a Nobel Prize was issued for the model because it basically created the option industry. And just some interesting history. Black and Scholes were having trouble with the math. Okay, and they called on a guy named Robert Merton to help them with the math. And so anyway, they come up with this model, and then like 25 years later, they decide that the economics Nobel Prize should go for this model. I don't know why it took 25 years, but in the intervening time, they gave the Nobel Prize to Myron Scholes and Robert Merton, who helped them with the math, and Fisher Black didn't get the award. And the reason Fisher Black didn't get the Nobel Prize for this model is Fisher Black died. And the moral of the story is if you're going to do something great, try not to die, because you don't. It's not offered posthumously. Okay, so that's the way it went. But it's a technique for price, and again, it's European style options. When the stock can be traded continuously, and it can be derived from the binomial option pricing model by allowing the length of each period to shrink to 0 and letting the number of periods grow infinitely. So again, the binomial model and the Black-Scholes model have to link to the same price, and they're ultimately tied together. Okay? All right, so here's the equation. And this is important to know, not for you to solve, but important for you to know that it's a very simple equation which we can put in Microsoft Excel. And here's the stock price, and there's some probability terms involved. And here's the strike price, right? K is the strike or exercise price. And there's a couple normal distribution probability terms in there. And that basically that's that for that. So you just got to know that again it's on a non-dividend paying stock, right? That know that, and it's on a European option, right? And here's the equations for D1 and D2 to help with the volatility. Okay, this is the standard deviation in the equation. And by now, people in the class, when we're in class, start going nuts, but they shouldn't get too nervous about this. Okay, so here's the normal distribution that I was talking about, and okay, so here's a nice multiple choice or true/false question that's related to the Black-Scholes. Only 5 inputs are needed to calculate the call or put option on a Black-Scholes equation, right? And here they are, all right? The stock price, the strike price, the exercise date, the risk-free rate, and the volatility of a stock. Okay, so you only need those. And here is a example from your book on calculating an option with Black-Scholes, and they happen to use JetBlue Airways, which is the airline that my son is a pilot for. And they go through it, and it's intuitive to go through because it's real simple. But if you want to go through it, and here's the JetBlue option quotes. So they go through all this mathematics, and they come up, when all is said and done, that the price of the call is 50 cents a share times 100 shares, right? That would be what, $50, right? For the because remember, it's 100 shares per option contract. And in table 21.1, the bid and ask prices for the option are 45 and 55, so it's right there, kind of in the middle. All right. So you can see how they go about with this math, and they get somewhat close. Okay. And again, remember what we said. There's an intrinsic value, which is the blue line, which is just the stock price moving here and giving you intrinsic value. And you'll notice that the Black-Scholes curve, the red curve here, is a little higher because what does this got, the red curve, have that the intrinsic value curve doesn't have? And that's the time value of the option. Okay, so there's time value of the option, and you'll notice that the time value gives more value to the call than just the intrinsic value does. Okay, so it's an important idea, and it's important. So you notice this all this time in here is the time value. Okay, so again, it's on. You could do it with European put options. Again, it's on a non-dividend paying stock. And we talked a little bit about put-call parity, right? And we said you can solve it for the Black-Scholes equation for puts, or you can just use put-call parity. Once you know the price of a call, you'll know the price of a put. But here's the value of a European put option. Okay, so and here's a nice example that they go through, again for JetBlue, on a put option. And they go through all this math, and they come up with it's 87 cents per share times 100 shares. That would be $87. And here's the numbers from the table. So you can see it's kind of like right in the middle. So it's within the bid-ask spread, right? So again, here is the intrinsic value for the put, the blue line, which doesn't include the time value of the option. And here is the red Black-Scholes curve from what we just calculated, and for different stock prices, and that will give you the include the time value. So you can see there's a little more put value there. So it's an important idea, okay? So another point I want to make is with the little mathematical logistics here. you can value a dividend-paying European call option with the Black-Scholes formula, and they do that here in this example here. And again, they go through the math, which gets a little messy here, right? But you can see here now what happens is when the stock price is sufficiently, as in this interesting case, is when the stock price gets higher, the call is worth less than its intrinsic value, okay? Because of the dividend. All right, so pretty much I think that's all you really need to know. And what I like to do is add a little extra stuff to the video from another video from YouTube, which I think will enhance everything we kind of talked about a little bit here. I hope it goes in, but I'm going to try to do that right now. And if you have any questions, email me, and I'll send you. I'll put some papers up on the blackboard on the history of Black-Scholes. Alrighty, everyone, stay safe. I'll talk to you.
In this video, we're going to take a look at using the Black-Scholes option pricing model to value options. Now, in order to follow along this video, it's probably worthwhile to stop, pause the video for a second, and go get a couple of files that I posted up on Google Docs. I used the tiny URL to keep the address a little bit smaller, but if you go, the Brocker-standard normal table is just a standard normal distribution table that we'll use as part of the calculation. The BSOPM file is just a formula sheet with the Black-Scholes option pricing model formulas on it. And last is a spreadsheet. After we walk through this by hand, you might find it's a lot easier to use an Excel spreadsheet. If you want to do that, the spreadsheet that I made up walks through the Black-Scholes option pricing model. You plug in the inputs and it spits out the value of the options, as well as some other information that might be useful as you get into options analysis. So if you want to pause right now, go get those files, and then come back, we'll start the video. Now, when I started this video, first thing I did in the setup was take a look at some current option prices. And this video was made around early June 2011. And I went and looked June 4th at Netflix. Netflix was currently trading for $273.40. And you can see the different options, some calls and some puts, widely different prices. Where do those prices come from? How do traders decide what's a fair value to pay for an option? One of the basic models is the Black-Scholes option pricing model, and that's what we're going to walk through in this video. Now, as we discussed in a previous video when we talked about intrinsic value and speculative premium, option prices are a function of 5 factors: the underlying stock price, the exercise or strike price for that option, the time to expiration, the volatility of the underlying stock, and the risk-free rate of interest. And those are the 5 factors that are going to go into the Black-Scholes option pricing model. So we're going to take all 5 of those factors and use the Black-Scholes option pricing model to figure out what the option is worth. We're going to start with the value of a call. Now, the formulas for the value of a call look pretty messy, and the Black-Scholes option pricing model was developed using stochastic calculus. I've actually seen the proof and walked through it once before, but mathematically it's a little bit beyond my skill level, so just let's trust these guys and assume that all these formulas are valid. We start with the value of the call, which takes the stock price times an area from the standard normal distribution table minus the exercise price divided by E to the risk-free rate times time. Now this looks like a big mess here, but really all that is a present value. It's the present value of the exercise price discounted back to today at the risk-free rate of return. The difference between this and normal discounting that you might do on a financial calculator is Black-Scholes used a continuous discounting model, so this E stands for the exponential. And then we take this and multiply by ND2, which is another area under the standard normal distribution table. Now in order to get D1, or the value of the call, we need D1 first, and so we've got a formula for D1 that looks like this. It's the natural log of the current stock price divided by the strike price plus the risk-free rate plus 0.5 times the standard deviation of the underlying stock squared, all that times time divided by the standard deviation times the square root of time. Now a couple things I want to mention here. First, whenever you see this T for time in the Black-Scholes option pricing model, it's going to be the number of years. So if we have an option with 1 month to expiration, that's 1/12 of 1 year. So we always have to plug that in as the number of years. Typically it will be less than 1, it will be some fraction or a decimal. The other thing is the volatility. Now we don't know what that volatility really is, so this is our best guess of how volatile the stock is going to be over the upcoming time period. But we want to make sure we plug that in as a decimal. So if we forecast a standard deviation of 25%, that would go in as 0.25. And our last formula, finally have something relatively short, D2, and that's used up here in the second half of the value of the call formula. That is just D1 minus the standard deviation times the square root of time. Now, in order to walk through the Black-Scholes option pricing model, the best way is to set up an example and go through that. So let's start with an example. We've got a stock that's currently valued at $62, so our stock price is 62. That's the P0 in our formulas. The exercise or strike price is $60. Since we're looking at a call, this option is currently in the money. If it expired today, we would exercise it. It has an intrinsic value of $2. So we know the value of the option is going to be higher than $2, but how much higher? What is the speculative premium that should be attached to this option? That's what we're going to find with the Black-Scholes option pricing model. Time to expiration is 40 days. Now remember, this is fraction of a year, so when we plug that into the formula, it's going to be 40 over 365. 40 days out of 365 days per year in order to set up time. Volatility, 32%. And again, when we plug that in to our formulas, it's going to be 0.32 and the risk-free rate of 4%. And when we plug that into our formulas, it's going to be 0.04. So our percentages have to be plugged into the decimals or into the formula as decimals, and time should be as a fraction of a year. Now that we have that set up, let's go through the calculations. When we set up our initial D1, you'll see the formula here, the natural log of this current stock price divided by the strike price plus the risk-free rate plus 0.5 times the standard deviation squared times time divided by the standard deviation times the square root of time. Now it's just a matter of getting out your calculator and walking through these calculations. Take 62 divided by 60, press the natural log button on your calculator, you'll come up with 0.03279. 0.04, just carry down. 0.32 squared times 0.5 gives us 0.0512. And 40 divided by 365 It's going to give us 0.10959. Now 0.32, 40 divided by 365, take the square root, gives us 0.33104. So all we're doing is we move down this step. It's a little bit of the calculations. Again, more calculations. Taking 0.04 plus 0.0512 gives us 0.0912 times the 0.10959, and our 0.32 times 0.33104 gives us 0.10593. Last step, add all this up, we get 0.04279, divide by the 0.10593, and that gives us 0.404. So our D1 is 0.404. Now we need D2. D2, remember, was our much simpler formula, just D1 minus the standard deviation times the square root of time. So we've got D1 here, what we solved for in the last page, times the standard deviation, or minus the standard deviation times the square root of time. Again, just go through the calculations. 0.404 minus 0.10593 gives us 0.298. Now we're going to have to look these values up under a standard normal distribution table. And the standard normal distribution table that I've set up carries everything out to 2 decimal places. And you might have went and printed that out from Google Docs. You can see here what we've got. Standard normal distribution table. We've got column of D's, column of ND1s, and we want to find 0.40 and 0.3. So if we look at that, 0.40 on this gives us a value of 0.6554. 0.30 gives us a value of 0.6179. So those are ND1 and ND2. Once we have those, now we can go back to the value of the call formula. If you remember when we introduced the formulas, we said that the value of the call, let me just find that formula here real quick. The value of the call was equal to P0 times ND1, which we've now looked up, present value of the exercise price, and ND2. So we set those in, P0 times our ND1, present value of the exercise price is 60. To get the present value, we take the risk-free rate times time, press the E button on your calculator. It's referred to as the exponential. Should be a little italicized E somewhere on your calculator, something like e to the x. So figure out what x is, and then press your e to the x button. And then we multiply by ND2. Go through the calculations. 62 times 0.6554 is 40.63. Our exponential is 1.004393. So 60 divided by 1.004393 gives us 0.6179, or 59.74. Now here's a little tip. Sometimes I have my students do this so they can see that there's nothing mystical going on with that present value of the exercise price. Just take your financial calculator, set it to 365 periods per year, so you're using daily compounding, and then 40 as your N. Our risk-free rate was 4%, so set that up as your interest rate. We're solving for the present value. The payment, there's no annuity stream here, so we're going to zero out the payment, and then we'll enter our future value, which is our strike price of 60. Solve for PV, and that should come up real close to the 59.74. My guess is it's going to be within a penny of that 59.74, because all we're doing here is finding a present value using continuous compounding. Daily and continuous compounding are going to be very close. So 40.63 minus 36.91 gives us $3.72. Now, if you're watching this video, I strongly encourage you to go through the calculations, practice this, and make sure that you can get the answers. Next, we're going to have the value of the put. But I'm going to stop here and save that for our next video. So in the next video, it'll be real short. We'll walk through that value of the put calculation.